Okay, guys, so let me go back to what we ended off with on last Thursday, and then we'll jump into learning about the machine cycle, storage devices, and what to look for when you're shopping for a computer. So as I always like to do, I'll talk about the theory, and then when I get done discussing a topic, we'll move into the practical side of it. That's taking what we've learned and applying for it, or applying it, if you will. So one of the things we're going to theory is when we go looking for a computer, how to customize it and build a computer that meets. Okay? So money becomes an object. In fact, if money wasn't an object, then why offer choices? You want nothing but the best, correct? But we offer choices because money is the object. So we want to try to make sure the choice that we make gives us the best bang for the buck. In order to do that, we're going to have to go back and just re-explore some of these topics that we left off on last Thursday. If I remember correctly, last time we met, we were building up a table of what are the 7 factors that affect a computer's performance. And one of the things I said is going to be what we call clock speed. Now, when you go shopping for a computer, they might not say clock speed. They might just say processor. And in there, there's going to be a follow unit. So, but more importantly, know what the units are. Like if I say feet, miles, inches, you're thinking that's what? Distance. So when you start seeing something with a hertz, now I say something because back when I was getting into computers, processors were measured by megahertz. Today we're measuring them by gigahertz. Will it be possible they could be measured by terahertz? One can only wish. But for all intents and purposes, if you see a number followed by gigahertz, it's going to be representing the speed, a cycle. In fact, what is the cycle when it comes to a computer? The machine cycle consists of 4 steps. Remember how we define a computer, IPO. The input-output are stuff that you and I use to interact with the computer. It's the P that's really the focus. The P, the Trinity, if you will, deals with the CPU, memory, and storage. The only reason why we have storage is because this component here is volatile, meaning this component requires electricity to keep data alive. And when the power goes out, we lose everything. Is it possible in the future that these storage and memory components could come into like one device? We're driving at that. We're calling it memory RAM or MRAM. And so that when the power goes off, you don't lose what's in memory. But for now, the process is simply this. The computer has to fetch data. The first place it's going to fetch it is going to be right here. Why? You got to just try to look at this as far as speed is concerned or performance. This is probably about the fastest component in your machine. The next thing is going to be here. And then the last thing is going to be there. So if you give this priority, faster, fast, slow. Okay? And remember, it's all about those zeros and ones. Those zeros and ones are going to be represented differently at each one of these states. So the first step is fetching. Well, in order for me to show you that, I need to show you what the architecture of a computer is. This is a single core. This area here is called the cache. You can think of it as the waiting room, the place where data goes to wait while it's being processed. This part up here is considered the control unit, and this part over here is considered the ALU. The job for the control unit, remember this is the CPU, is to go out and grab the data and or instructions from the memory. So the CPU is going to, the control unit on the CPU is going to come out and grab the data or instructions and load it into the cache. What if the data or instructions weren't in memory? What if it's the first time your computer boots up and you want to write a program like Internet Explorer? Well, what's going to happen is we're actually going to have to go to the storage device like your hard drive or your flash drive, load it into memory, and then from memory, load it into cache. Seems a little funny that we're taking the data, copying it here, then copying it here. Why would we do something like that? Yes, Adam?
You kind of remember the sites and things that you've been to?
Yeah, you're getting a little too far for me for Internet Explorer, the history thing. In fact, let's not even say Internet Explorer. I can say any program like Photoshop or something. Programs are becoming more and more intelligent. They're evolving. They're doing a lot more. Back in the day when you opened up a web browser, all you probably could have done is look at text and maybe a picture. Today, you guys can play games within the web browser. So that's the evolution of today's modern web browser. And in order for software to evolve, the instructions, the code, is going to evolve too. It's probably going to get complex, and it means the file is going to get larger. That means these applications that we use today are becoming much, much, much bigger. In order for it to be processed, it's got to be stored somewhere here on the computer. That's what we call the cache. This size right here is going to be very limited. We would love nothing more but to put everything on the CPU. One chip. Storage, memory, processing. Because then everything's working with zero bottlenecks. See, each of these pathways are going to create bottlenecks. This is the slowest. So in essence, you can only work as fast as your slowest piece. So what could we do? We could create like a buffer area that while the data is coming in and being processed, I don't know, fragment at a time, segment at a time, that more data is loading into memory, and then that data is loading into cache, and then back around again. Think about it as like riding a roller coaster. Only so many people can ride that roller coaster at one shot, correct? You have this really long line, and then that line, right before you get on the roller coaster, is then divided by lanes per seat of the roller coaster, correct? So you can think of that as the cache. Because we want to try to get those people on that ride and off that ride as fast as possible. Because the quicker we can improve that process, the more people can ride that. Correct? So the long line is here, working its way to memory. That's those lanes. And then obviously the roller coaster would be that process of enjoying it, correct? So as data is being carried from the control unit, grabbing it from the memory and putting it into cache, the cache is going to then store it. And it's going to store data in two forms. Data itself and information, if you will. So the first step is fetching it. It might have to grab it from memory, and if it's not in memory, it's going to have to grab it from the storage device. Next step. Whoops. Decode. So the second step is going to also be handled by the control unit. The control unit has to determine whether or not this was instructions or if this was data. What's the difference between data and instructions? Instructions tells the ALU what to do to the data. Like when you guys click on a hyperlink, your command, your click, is going to be instruction that says open this link, correct? The data is going to be like the web address. The instruction is going to say when you click on it, either open up a new tab, open up a new window, or load the page in an existing window, correct? So when that click comes in here, that click's going to be right here in memory. The control unit's going to grab that, put it in cache, or as your online textbook will call it, registers. And then the control unit will read that register and say, oh, this was a command. So then after it determines that it's a command, it's got to do what the command says to do. Execute. That's what the ALU is for. The ALU is short for the arithmetic logic units. It's a bunch of math. In fact, most computers are built with 86 core instructions. Now we have added to them over the years. And so when that decoding process is occurring, it's matching that instruction set to one of the 86 core commands. And those 86 core commands can be executed right here in that part of the CPU. In fact, you guys did this last week when we were doing our index cards. I said doing this index card was designed to illustrate what a computer does. Let's look at this for a second. First thing was fetching. What did we have to fetch when we did our index card? Remember, the index card was you had to write your name across the top, then you had to write it vertically. Where did you get your name at? Yeah, it was stored deep down inside. Now, that becomes questionable. Is it memory, like conscious, or subconscious? How long does it take for you guys to think about what your name is? Not very long. It's there, correct? However, if I tell you, could you guys remember what happened in season 1 of The Walking Dead, first episode? You might be thinking about, well, where the hell did that come from? Or secondly, you're just going to be like, season 1. And then as we start talking, think about that. As we start talking about it, some things start firing up here. And then that starts coming to life, starts coming to your consciousness, starts getting loaded into memory, and then everything starts flying. I mean, if you're really excited about that TV show, your mouth will go a mile a minute. Oh yeah, that's right, that's what happened, this what happened, and blah, blah, blah. But before you even thought about it, it was stored deep back here, and then you had to try to dig that up, and that was a long process. Just like when you're trying to think of somebody's name, it's on the tip of your tongue. And then 10 hours later, oh shit, that's what his name was. Deep, deep consciousness, right? Right there, up front. So when you guys had to fetch, you had to fetch your name. Correct? Then I told you to do something with that. You had to decode it. You had to convert your name into some numbers. What did we use to do that? A chart. These computers are going to have that. They're going to have some kind of core instructions, a language that they understand. We call that machine code. So then I told you guys you had to do something with that then. I taught you something. I taught you how to divide or how to convert a decimal number to binary, correct? Now that binary is important because that binary is going to basically tell me how to store that in here, how to store it here, how to store it here. It's also going to tell me how to manipulate it, how to process it. So I gave you some instructions, and it's funny. Wasn't they just mathematical instructions? Divide, count, glue them together. Arithmetic logic unit. Was that process slow? Manually going through and dividing each of them? Could we improve on it? Yeah, I will show you a shortcut. One where you guys can manipulate decimal numbers to binary numbers in a few seconds. That leads to another factor of performance. Now, after you guys got done taking that and converting it into a binary number, what did you do? Remember, that was being done right here, on the back of the card, if you will. As far as these two things are concerned, they're one and the same. This is just a lot faster. In fact, cache is measured in megabytes. RAM, or memory, is measured in gigabytes. Now, they're still bytes, correct, folks? So we have mega in cache, giga in memory, but all they're doing is holding data waiting to be processed, or data that was processed in information and waiting to be sent back out. So fetch, decode, execute, store. And that's when you guys flip the card over and you wrote it up front. And that's the life of a computer. In fact, this is the machine cycle. And when you 3 gigahertz, this stuff that's occurring right in here is happening 3 billion times a second. Fetching, decoding, executing, storing. Whether it's being stored here, here, or there, all depends on how permanent it needs to be. So what else could we have done to make that process faster? When we're doing our index card, what else could we have done to make it faster? Would a bigger card helped? I told you all your work must have been done on that card, right? So when you guys flipped that card over and you wrote really small because you weren't sure how much space it was going to take, when you write smaller, doesn't it take a longer time to do it? Harder to read? So would it, in effect, a bigger index card be easier? In fact, that's why I love my whiteboard. I'm really inefficient about using my whiteboard space, but it's faster for me to jot an idea down. The back of that card is representing memory. The more memory we have, the better off we are. Because the less trips this has to occur. See, we want to try to keep this information flowing from storage to memory, from memory to cache. While this stuff is being processed, it's going to grab it off of here. And if we can just keep it going from here to here, which uses what we call the front side bus, which we'll explore later, the less waiting I have to do. I guess in a way you could think about it as a funnel. You have a really, really small container, correct? And so you use a funnel with a big opening. But as you take your huge container that contains your fluid and you pour it into the funnel, what do you have to be careful of? Overfilling the funnel, correct? So the larger the funnel, the more we can put into it, correct? Now, you're thinking a container, the container would fill up. Just imagine a little hole down at the bottom of the container, correct? And that's what's happening here. You're filling this up, it's being processed, and then it's being let out. We okay with that? So the more memory we have, the more data can get into here, saving us time in here, because while I'm loading up my movie, a half of it might be stored here, the other half might be stored here, and the first 2 seconds are in here. 2 seconds are processed, sent back to me so I can watch it, the next 2 seconds, and the next 2 seconds, and the next 2 seconds, or 2 minutes. Obviously, the bigger this is, the longer the clip is for the movie. So hence, the more cache we have, the better the performance. Now, does this really matter when it comes to processing text? Question.
I don't know. Yeah. So, is that considered all the steps or just like the top
Don't think about these as steps. These are factors for performance. So when you're shopping for a computer, these are the things you want to look at. And obviously you want these to be great, bigger. So you want more gigahertz, you want more memory, and you want larger cache space. And these units here are typically megabytes or gigabytes. So larger is better. This is just the cycle, letting you know how data is traveling to be processed. So the first part is stored in storage. Then you have to fetch it. Hopefully it's in memory, but if it's not, you have to go back to your hard drive, making it a lot slower. Now that's why when it comes to factor number 4, I won't say the size of your hard drive. To me, sizes of hard drives are irrelevant. When you look for that, you're just basically determining, are you a video user, video game player, just an internet user, word processing, email? What do you do with your computer most of the time? Do you store a lot of pictures? Do you download a lot of music? If it is, then what it comes down to, and then it's getting to the point where it's really trivial. I mean, 2 terabyte hard drives, you can get them on sale for $70 now. And so I tend to ask my clients, how much are you willing to spend on a computer? And if I have to give or take, I'm looking at a 2 terabyte hard drive and I'm saying, it's only $70. Why not? I don't care what you plan on doing it. And even if you only use an ounce of all that storage, doesn't hurt to have it. And that's the truth. It does not hurt to have all that space. You never know when. Now, if I have to make a decision between $40 and $70 and that $30 is going to make me improve my memory, I would choose the memory performance over the hard drive. Because you can always buy external hard drives later. And they get cheaper and cheaper to the point where if they can't get any lower, they just increase the number of terabytes. So I don't look at hard drive space as the number one factor when you're shopping for a computer. In fact, when it comes to storage device, I'm looking at storage speeds, which I'll call transfer rates. And I believe we were talking about how we're getting that to be manipulated. It might be gigabits per second. Now, if it's storage transfer rates, then I might have to look at something. I really don't focus too much on the RPMs because we are moving away from magnetic storage hard drives to solid state drives, like your flash drives, where we don't use spindles. And solid state drives are great because there's no mechanical parts, and if there's no mechanical parts, the hard drives won't wear. Hard drives will crash. If you're a really aggressive user, expect about 2 years. If you're just adding files here periodically, 5-6 years. They are getting better. But I do throw that in there because when we go shopping at the end of class today, that might come up. Now, transfer rate also has a big effect when it comes to this too. Now, to give you an idea of the transfer rate, going back to the index card, now be honest with me. You had to write down 8 zeros and ones per letter, correct? When you were transferring it from the back of the card to the front of the card, how many zeros and ones were you carrying? Like, were you like 001 and then flip 001, then flip back 001 again, 001? Were you doing it like 3 bits at a time, 4 bits at a time? Did anybody do all 8 bits? Obviously, it would have went a lot faster if you could do all 8 bits at one time, correct? It's because you only flip that card once, write them over, flip back, and get the next letter. But if you're doing only like 3 bits, then you're flipping that card 3 times. Actually 6, you got to flip it forward and backwards, right? So 6 times. Well, that's where the word length comes in, and that's how it's appropriately named, because what is a word? A bunch of letters glued together, correct? So the more letters you can do at one time, the faster the processing. This is measured in bits. An example of this is going to be like 32 bits, 64 bits, and 128 bits. Now, when I was a kid, the NES first came out, and from there it was like all downhill because NES was like 8 bits. And then the Super Nintendo came out, and then we had to convince our parents that this was the thing to get. And Nintendo versus the Super Nintendo, well, Mario looked a lot better. I mean, you had Yoshi. But the sound was better, the graphics were better, but why?
More bits.
More bits. It went from an 8-bit to a 16-bit system. And think about it, 16 bits. 16 bits would allow me to represent 65,000 unique colors. 65,536 colors. 8 bits would only allow me to represent 256 colors. That's why the old Mario looked pretty flat. Only a few colors in the palette, correct? Then we went from Super Nintendo to what? Nintendo 64? And the reason why I went from Nintendo 64 is because PlayStation and Genesis came out and they were 32-bit. But they were CD. And everybody thought that was the greatest thing because they were CD. But technically, the Nintendo 64 was better because it was a 64-bit palette. But you and I wouldn't be able to know the difference because what was the limitation for the eyes? You can only see 16.8 million colors. So 24 bits was more than enough, correct? So after 32 bits, it seemed frivolous. But today games, they're up to like 256 bits. Well, that comes to this. Because the frame rates of these games are like 60 frames per second, which makes it even more realistic. Now the frame rate's how many frames you can see, or how many pictures are taken in 1 second, correct? Obviously, the more pictures are taken in 1 second, smoother something becomes. You good about that? Ironically, the human eye can't see anything beyond 30, 32 frames per second. But when you create video games, it's artificial, and you have to double it. So anytime something is generated or created, you have to just double it to make it sound more realistic, to make it look more realistic. So that's why when you're playing video games, the target frame rate is 60 frames per second. Anything beyond that is just a little too much. So we look at the word length. We want these larger word lengths because we know that we're processing more bits at the same time. Here, 32 bits is allowing me to process 4 letters at once. 4 letters. Were you guys able to process 4 letters at once? Here, if I go to a 64-bit processor, it allows me to process what? 8? 8 times 8 is 64, right? 8 letters at once. But more importantly, remember, these bits are also used to understand different combinations. And you got to pay attention because this is what's going to affect you when you shop for a computer. Do not buy 8 gigs of memory when you have a 32-bit operating system. 2 raised to the power of 32 is 4 billion, give or take. Okay? How many bytes is 4 gigabytes? What's a gig worth? Billion, right? 4 billion bytes of memory is the most that a 32-bit operating system can address. That's saying that the operating system will only recognize up to 4 gigs of RAM. So if you go out and upgrade your computer to 8 gigs of RAM, you just wasted a whole lot of money. Because the operating system won't address beyond that memory address. Think about it. Every bit is like a little container that could be storing something on or leaving it empty, off, correct? Every data that needs to be processed has to be stored in those tiny little containers. If your computer can only address 4 billion little bits, or bytes, I should say, bytes, then your computer can't go beyond that. Hence, what's the reason buying more? Because remember what I said, buy as much as you possibly can with this. So that's why we're moving towards 64-bit operating systems, because we have larger memory banks. Why do we want larger memory banks? I can store more into here, which cuts back on the time between fetching and decoding, hence improving it. But that will only be possible if I have a 64-bit operating system. See a little catch there? So all these are in effect, they need to be harmonized. Number 6. Now, if I remember correctly, when I last met with you guys, I gave you my laundry example, correct? And then I said that when you're doing laundry, it can be handled in many different ways. Data can be processed in many different ways. It can be processed in what we call pipeline processing. That's like you start with the washing machine, push it to the dryer, and then you fold it. You see how everything goes into one pipe? Then it could be threaded. Pipeline. Yeah, I should have called it serial, but nevertheless. Then you get into this threaded, where you can say, okay, if I have 2 loads to wash to do, I can put one in the washer, wait a second until that's done, take that wash, put it in the dryer, correct? While the dryer's running, I can take the other load and put it in the washing machine, correct? But then I can run both loads at the same time. If I had what? 2 washers and 2 dryers, correct? A core. And maybe part of the cache, but it's mainly the control unit and the ALU. Remember what the control unit does. It fetches data from memory, puts it in cache, correct? It takes that data, decides whether it's instructions or something that needs to be processed. We good there? Then it passes it to the ALU. When you have multiple cores, each ALU has its own manager, its own control unit. Now the cache can be shared because all it is a waiting room. It's like going to a doctor's office that have 5 doctors, and each of the doctors have their own assistants. You're here to see Dr. Bob, you're here to see... Your time is ready. Assistants out, grabs you, and sends you to the right room. Clear about that? The more doctors is like having the more washers and dryers. The more number of cores, the more data can be processed. However, what about this pipe? What if there's a single lane dirt road going to the doctor's office or going to the washer, to the laundry machine? What's going to happen there? Because all those number of control units are all going to come out here and grab data off of memory. Correct? So if this area is slow, doesn't matter how many cores or how fast your processor is, because we're bottlenecking, because if the data can't come in here needing to be processed per core, then you wasted your money on that. So, number 7, which is dying off, used to be called the front side bus, and it used to be measured in what we call megahertz. In fact, that unit is now being built into memory. So this is actually coming up to here now. And the reason being is because the new school of thought is getting rid of what we call the front side bus and calling it the QPA. well, we'll call it controller. We have taken the memory controller, which used to be on north or south side bus, ripped it off and built it right into the processor. And the reason why we did that is because remember the processor has X number of hertz, correct? Whatever's being ran at the processor is running at that clock speed. We clear about that? That means the connection between memory and the CPU would now depend on the speed of the memory as well as the speed of the computer. No longer would it depend on a third middleman to coordinate the flow of traffic between memory and CPU. So now I say to you guys, when you're looking at this, go back to factor number 2. Make sure you can get enough of this as fast as you can get it. Okay? So factor 7, I'm just going to put a dotted line in there because there are processors out there that still use front side buses. And that's why I say there's 7 factors, because really number 8, although it's out of our control, has a big effect on what we do. It's called the instruction set. And it used to be so clear to illustrate this to students because when I first started teaching this class, Apple still had their own, actually they used Motorola processors. And then when I was teaching this, I go, there's a reason why Apples and PCs are different. They have different processors. And there's a reason why a lot of people in the graphics arts or web design business would choose Apple over PCs. And the reason behind it was because Apple's processors had a larger word length, but a slower clock rate. Now think about it. I used video games as an example for one reason. When it comes to processing text or numbers, that's all the business world. And that's why the business world used a lot of PCs. Because compare that to graphics, which one takes up more space? Images take up a lot more space. In order for those images to be processed, they have to be coming from storage to memory, from memory to the processor. It doesn't matter how fast your storage device was, how much memory you had, if this area here is really slow. So graphic designers loved Macs because they had a larger word length. The other reason why they loved Macs is because they had what they called the reduced instruction set. PCs use the complex instruction set. Here's an example. I'm going to do it on the other board. When you guys learned, using that index card, how to convert a decimal number to binary, this is the approach you took. Let's take 128 and convert it into binary. This is a complex algorithm. I take 54 and I divide it by 2 and I get what? 27, remainder 0. Remember, even number. 27, remainder 1. By the way, on your exam you will have to convert some numbers. Oh, let's see. And finally, my answer is going to be 1, 0. Where were you guys on that one? I obviously wasn't around. Math, arithmetic. Let's use some logic. Sure, I can make you happy. I was just saving time. Because remember, any 0 in front of the leading one probably doesn't hold value, but it is an 8-bit system. But we're just converting decimal numbers. Remember, that was to represent a letter, right? That's if you're using ASCII. But if I'm just converting decimal to binary, it's irrelevant. All right, let's look at it from this perspective. Remember we were doing the odometer and learning how to count? I said it's going to come back around on us. When we were in this first column, what did we call it? The very first placeholder. The ones. And what did we call the next column? Why was it called the tens? The first time we went over there was when we had to count to 10, when we were at 10, correct? All right, and you know I'm not going to write that in there yet because I want to convert a binary number or a decimal number into binary. So we'll get to that. What about this column? What was this called? Hundreds, right? And what would this one be called? What's 10 raised to 0? 1. What's 10 raised to 1? What's 10 raised to 2? And 10 raised to 3? Starting to see a pattern here? How many zeros existed after this one? 0. How many zeros existed after this one? 1. How many zeros? Right? What does 10 represent? Our base. Base 10, correct? But now I'm in binary. What's the base for binary? 2. Index 0. 2 raised to 0 is? Anything raised to 0 is what? In first place will always be considered the ones column. 2 raised to 1 is? 2. When do you think we go into that place? When do you think that's going to occur? When we're counting in binary? 0, 1. What's the next number in binary? So that was 0 in decimal. This is 1 in decimal, and this is 2, correct? What is this place going to be? 2 raised to 2 gives me? When do you think that's going to happen? Right? No different than decimal. So, we seeing a trend here? What's the next place going to be? Remember I told you about a guy called Moore? Gordon Moore? What was his rule? His theorem or law? Every 18 months, processing power doubles. You notice every time I add a bit, what's happening to my value? I add one more bit, what's going to happen? Oh. I add one more bit. What's it going to be? 1, 2, 3, 4, 5, 6, 7, 8 bits. All right? Let's convert that 108 back into binary. But we're not going to divide. We develop what we call a base place structure. 1, 2, 4, 8, 16, 32, 64. And here's where the logic comes in. You ask yourself, which one of these places comes up to 108 without going over it? What's the closest number to come up to 108 without going over it? Put a 1 in the 64. That's telling me that a 108 has a 64 in it, correct? How much is left over? 44? Which one of these numbers comes up to 44 without going over it? Closest to 44. Put a 1 in it. Which one of these numbers comes up to 12? Well, isn't a 12 an 8 and a 4? Give me any number between 0 and 255, and let's see how fast I can convert it. It don't match. Did I screw up over here? Oh, I must have screwed up. 6 divided by what? Oh. Now they match. Thank you. I screwed up. This is where Windows crashes. You get a blue screen. That's what I just did, okay? So a little bit more effective because you don't rely too much on the previous one. But give me any number. Help me out here. Adam, a number between 0 to 55. 97. All right, so that's a 1 here, a 1 there, and a 1 there. Because 64 and 32 is 96, plus 1 gives me 97. Another number. Tina, 0 to 55. Pick a number. 55. Okay, so that's a 1 here, and that's 23. 23 is here, here, and here. 16. Oh, you say what, 55? All right, so what's this? 16 in that is 48. That gives me 56, so I messed up there. And let's see. What's that? 48, 52, 50. Yep, 55. Do you see how the instructions affect how well your computer performs? I taught you this way because it seems simple. You divide, 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 string it up. This way requires some logic, correct? Which one of these numbers comes up to without going over it and put a 1 there? This allows us to jump, though. I didn't have to process every number. Here I did. Even if I got a 0, I still had to process it. This is why some programs run better than other programs, because their code is really efficient. Now, like I said, this is out of your control. If you didn't know about this, then how would you know to do it? You don't tell a programmer how to write their code. However, when you buy software, they'll do benchmarking, and they'll see how effective it is. And if Microsoft Office is more effective than OpenOffice, then it's the difference in how they coded. Is their code more native to the processor? Now, this happens quite a bit. In fact, when we get to operating systems, I'm going to show you guys a software called VirtualBox. Very nice tool. In fact, the biggest complaint I have today is that our hard drives are so massive that we're not using the way we should be using. You guys should be installing another copy of your operating system in what we call this VirtualBox system. And when you go out there on the web and you start downloading instructions or software that's unquestionable, and you put that on your computer that has all your pictures, and that virus starts taking over things, what is the only way people will fix it now? Because they don't manually go through them and check out all your... Because the price per hour is too cost ineffective. They say, sorry you lost everything, we'll reinstall things from scratch. By creating this VirtualBox, you only delete that file that contains the operating system, and you try again. So we'll get back into that. Now I bring that up to this point because this VirtualBox allows us to make a transition from the instruction set to the software. That is, I can install other operating systems within this operating system. And that becomes really imperative because only certain operating systems can run on certain processors. And this is why we used to call them Wintels, because it was Windows and Intel processors. And Apple did something that was rather brilliant and saved their company. They recognized that PCs had more software choices than Macs. And why was that? Because Microsoft was smart enough to realize that, you know what drives computers? Just like what drives video game consoles. Show of hands. If you had to buy a game system, would you buy the Microsoft 360 or Xbox 360 or the PlayStation? Xbox? Why would you buy the Xbox, Morgan?
I did buy it, and I bought it. There was a lot better games on it. A while ago. That's by the PS3.
Why is that?
Blu-ray.
Ah, so you're looking at the hardware.
Yeah.
Why? Never liked the Xbox. It was just perfect. But what about game titles? The more games that you play are on the PlayStation. Interesting.
You have free internet connection and PS3 also.
So now it's become services too. Anybody else want to get in this debate? It all came down to the titles. And the Xbox had a lot of killer hits. Microsoft realized that. But then Sony came out with their PlayStation 3 and they spent, literally every PlayStation they sold, they were losing like $300, $400. They were hoping to make it on the back end. That was through the games. And then PlayStation started losing traction because those exclusive titles, like Metal Gear or whatever, became open. Because as a developer, I was like, holy shit, why would I want to limit myself to one platform? Because look at the mixed audience. If I'm Konami, I want to make my game so it plays on the Nintendo Wii, the Xbox, and the PlayStation. Correct? Because I have a larger client base. And then Sony would try to approach them just like Microsoft would try to approach them and say, we'll give you X number of dollars if you make your game exclusive to us. Why would it matter though? Why would the developers have to rewrite their code? Because every hardware, every game console had its own unique processor and its own unique instruction set. And as a developer, we were just hitting our heads against the walls. Microsoft was easy to develop for because they kept to an Intel processor. By keeping to an Intel processor, the same games that people wrote for PCs were easily ported over to the Xbox. Greater software choices people stuck with. And Apple saw this and they realized that we're losing business because we don't have software titles. If I only have 5 choices of software to get on my machine, and PCs have thousands, if not millions of choices, who would you go to? Because a lot of us don't buy computers based off of this. We buy them if they can do things for us. Software manipulates the hardware. If you can't get your favorite web browser on your computer, this is why I have the biggest problem with like my IT lab, because I hate using Internet Explorer, but I have to use it. The next version of my IT lab is now supposed to be cross-browser compliant, meaning it's going to work on any one of my favorite web browsers. You see that thing called choice? So what Apple did is they got rid of the Motorola processor. And I was really embarrassed the day I said, I'd be shocked as shit to see that Apple would go to Intel. And a student brought that to my attention. And they did. And it was the best choice that they could have made. When they dropped the Motorola processor and decided to pick up Intel processors, they gained that x86 instruction set. This instruction set's really important because guess what? That's what Windows is built on. And now with Apple-based products, you guys can install, using Boot Camp, a version of Windows. So if there's software that you don't have on your Mac, you can always reboot it into Windows and have it there. See, Apple's a hardware company. That's why those iPhones are sexy. They focus their time on hardware, not on software. Microsoft is a software company. Apple got the best of both worlds. You install Windows on a Mac, and you get everything that PC people get, including viruses. That's mainly gamers. Because Apples have a very poor selection of game titles. It used to be that you had to have Windows to use Microsoft Office. But Microsoft has ported their Office program over into Apple. So then people are scratching their head and they're like, What does this all stem to? Why does it make a difference? Well, Apple has a big increase in sales, and PC's been losing a lot of sales. Why is it? How many people, does anybody own an Apple device? Okay, why? And don't tell me because it's cool and hip and it's the latest trend, because I think that's the reason why most people do it. But why do you own an Apple device or would like to own an Apple computer? Nothing pisses me off more than when my computer goes to a blue screen, or I have to install antivirus software, or I keep on losing everything that I saved because I got to clean out my computer because I went to the wrong website by accident, right? Now, is Windows getting better? Is Microsoft improving Windows? Absolutely. 7's a really good version. 8's supposed to be better. Ironically, 8 is supposed to be more cross-platform compliant. And that is the future of our devices. It drives me nuts that we live in this world where everything is just zeros and ones, bits and bytes, right? But now I got to pick a side. Whether you have a Ford, a GM, a Chrysler, a Honda, you go all to the same gas station. You use the same gas to power those motors. Correct? Why do I need to have millions of different devices and say, oh, I got to buy this app for this device and this app for that device to do the same damn thing? Because in my house, some people like Windows, some people like Mac. They're all zeros and ones. And guess what? They're all affected by these factors here. And to show you this, we're going to go shopping. And we're going to see why most students own Windows and why they don't own Macs. Because Apple puts a huge price tag on just their name. So let's find out once this pops up.
My brother-in-law has an iPhone, and my wife and I have he's got a big we have probably just as many extra deals as we are. They're all
there are, and you brought the language up, so we'll get into that. There are free apps, and it all is the developer, and, Apple's got to get their little slice and things. Google has a really open philosophy, at least I should say they had an open philosophy. That is changing now. They're starting to take away Google Apps, and they're starting to charge people. Folks, anytime you go public and you have to answer to shareholders, and especially when your stocks take a huge dive, it doesn't become about functionality anymore as much as it becomes about profitability. So let's get into this, and we're going to explore two worlds, Apple's, and by the way, I am not condoning one or the other, okay, folks? You're going to make your choice. But what we're going to find out is that the factors are going to be the same, all right? So this is going to be an Apple-based system, and Apple can charge more because their operating system is wonderful, and we'll get into their operating system when we get into OS. But when I go look at these right off the bat, I see I have $2,500, $3,800, and $3,000. Now, obviously, price is going to be a concern. But let's compare these models to see if there's a difference. First thing, this one has a 3.2 gigahertz. So that's the clock speed, right? It also says this is quad core. That's this factor right here. Number of cores. Let's look at this guy. 2.4 gigahertz. Let's ignore that there's two processors. But 2.4 versus 3.2. Just looking at the gigahertz, which one's faster? Just looking at the gigahertz. The 3.2 is a bigger number than 2.4. However, one could argue, well, there's two of them, right? So 2 times 2.4 doesn't work like that. Okay? Like your index card. I believe Mitch and I shared a few letters, like the C and H. I could have said to Mitch, okay, I'll do the I, you can do the C, and then I'll do the H, right? Trading some things up, help save on some time. But there had to be some coordination. That coordination will affect performance. So you can't double it there. But this is 6 cores, and that's 4 cores. Just looking at the number of cores, which one do you think is going to be better?
6 cores.
6 cores. Dependent on what? Large amounts of data, correct? Because if you're doing simple text stuff, you're not going to notice a difference between these two. But if you're dealing with like 18 megapixel camera pictures or high definition movies, then you're going to notice the difference here. Because the more washers and dryers that I have, the more laundry I can get done. But if you're doing a load every day, what's the point of having 6 washers and dryers? It all depends on your usage, correct? So let's go down to the next one. This says 6 gigabytes of RAM. This says 12. Is 6 good enough for you? 6 might be a little too much for you. Once again, get to know your usage. Do you plan on multitasking? What do I mean when I say multitasking?
Listening to music while you're taking education.
Running 2 or more programs at the same time, correct? What is the difference between multitasking versus multi-threading? Remember, I taught you multi-threading by using laundry. The task was doing laundry, correct? The task had many threads. Organizing, washing, drying, folding, correct? Task, 4 little threads. Multitasking is when you're doing 2 things, like cooking dinner and doing laundry. Like watching TV and doing laundry. And that's why I love having loads and loads of clothes. Because I'll download all my TV shows, leave them on the server, and when it's laundry day, which I can't wait, a couple more weeks, I'm spending 16 hours doing my laundry. And you know, this is the other time saver. I don't watch the commercials. Do you realize a 1-hour TV show has like 22 minutes or 20 minutes of commercials? So that means for every 2 shows I watch, I get the 3rd one for free. Right? So every 2 hours, if you will. So that means I get the 3rd one for free. So I can watch about 12 episodes. No, more than that. If I'm doing 16 hours of laundry. So I can watch about 24 episodes in about 16 hours. Allows me to catch up with the latest stuff going on. Ask me anything. You guys want to talk about Walking Dead, Justified, Mad Men? Let me know. I won't be able to talk to you about the latest episodes. I can tell you about last December. But wait until the end of February when I do my laundry that, I'll be caught up. But that's multitasking, right? Because when you're folding clothes, do you really have to pay attention to what you're folding? It's only my clothes, so it's not like I got to, separate her underwear from my underwear. But, you getting the idea? So, getting back to this point, though, if you have loads and loads of clothes, you better have a big-ass laundry room, right? But if you have a small amount of clothes, or if you do clothes once in a while, and, my closet, it's got to be retrofitted, because I don't throw away my clothes. I just add to it. And I have hangers and hangers. I was, so grateful when they brought out those 4-tier hangers, pants inside pants. I mean, that just, tripled my space. But ideally, I need a bigger closet. I need more room. Because when I go through those triple hangers, I'm like, oh, my 3rd pants, the black ones are in the middle. Takes a little while. So more memory, the better off you are. But that's dependent on you, the user, if you feel that you're going to be processing large amounts of data versus smaller amounts. You notice 1 terabyte, 1 terabyte? But over here at the server, they say 2 terabytes. Why would the server have lower processing attention, and lower memory, but greater storage? Servers are centrally located, and more than one user are using it. If it's only you in your house, it's sort of ridiculous having a server, correct? But if there's 7 people in the house, then it makes sense to have a server. just like there was a lot of us when we did our little file management exercise. Hence, you're going to be storing a lot more. Okay, they talk about this stuff, which we're going to get into Thursday, about storage, and then they talk about graphics power, which they're all across the same. And we'll talk about the GPU and how that's affecting and how things are changing from the CPU to the GPU. But for all intents and purposes, we talked about the clock speed, the memory, but we haven't talked about the cache, right? The cache is located on the processor. Let's choose this $2,500 one. And now they're going to break it down, allow me to scale things according to my needs. Let me hit Learn More. And they're saying that it's a fully shared 8 megabytes or 12 megabytes. So the first processor I choose is 8 megabytes of this waiting room, if you will. Obviously, the one I would really like to have is 12 megabytes, correct? But you notice the 12 megabytes is going to be used for the 6-core processor, not for the 4-core. In fact, do the math. What's 12 divided by 6? 2? What's 8 divided by 4? Is it safe to say that each core is getting 2 megabytes of cache? Would it be nice that the 4 cores could have 12? Well, don't get ahead of yourself. You don't buy a bus when you only have a family of 4 people. Would it be roomier and easier for the kids to have space? Absolutely. But is it overkill and it's not going to be used? Yeah. If you're going to increase the processing clock speed, then you want to have more cache memory. Okay? All right, so we got that out of the list. Clock, memory, cache. Oh, transfer rate. Where did I say that's going to be a real impact? Transfer rate. Where is that going to be affected? Looking at the P, looking at the triangle. Is it going to be between the CPU and the memory or between the storage and memory? Actually going to be in both places because transfer rate is what it says. When you are going from storage to the memory, it's got to be transferred, correct? And when you're going from memory to cache, it's got to be transferred again. So let me go down to the hard drive for a second, and you'll see right on that line, it says 3 gigabits per second. What did I tell you the units were for transfer rates? GBps, right? We are moving away from the 3 gigabits to 6 gigabits per second. However, did you see Apple did not offer that as an option? The question might be why. This is a magnetic hard drive that has these platters that are spinning. The faster the platters can spin, the faster they can retrieve data off of them. The faster they can get data out of the hard drive, the sooner they can get to memory. In other words, the faster you can find files in a filing cabinet, the quicker you can get to your desk, correct? It would be overkill to offer a 6 gigabit hard drive at 7,200 RPMs. Because your platters are still spinning at a constant rate there at 7,200. And it's got to get that data off those platters. And so hence this becomes the bottleneck. What they feel is this is a pretty good relationship. We good about that? If you want 6 gigabits per second, you might want to get 10,000 RPMs. But remember what they say. The candle that burns twice as bright burns how long? Candle that burns twice as bright burns half as long. The hard drive that spins faster lives a shorter period of time. That makes sense? So what are we trying to do? We're trying to get rid of that. We're trying to go to solid state. Do you notice this is 1 terabyte, and that's 512 terabytes. Sorry, gigabytes. I wish it was 512. 512 gigabytes. But they're saying to add this option, it's going to cost you almost $900 more. Looking at the storage units, which one can hold more data? The 1 terabyte or the 512 gigabytes? 1 terabyte, because that's 1 trillion bytes, correct? This is 512 billion bytes, billion. So this is literally half as this hard drive, but they want to charge you $900 more. Why?
It doesn't have to go through that process. It's just
There is no RPMs here. The solid state hard drives use little tiny transistors. We call them AND gates. Or NAND gates, whatever. We'll get to it. But nevertheless, when the power goes out, it holds the memory. It holds the data, which is a plus. But each of those bits can be referenced. So instead of spinning that hard drive and trying to find it, seeking it, where it's stored, and grabbing it, it knows exactly where it is, and it jumps to it, which we call random access. So the transfer rate for these drives are huge. The other thing that makes those drives nice, there's no wear and tear to them. Hard drives have moving parts. Solid states do not, hence the word solid. So very durable, extremely fast. However, they're extremely expensive to make. And because they offer more performance, they're going to cost more. Does that make sense? You guys will be eventually in your lifetime moving to this. If you own an iPhone, an iPad, a Droid device, any one of those kind of components, they use solid state memory. Your digital camera with SD cards or compact flash cards are all solid memory. And you could beat the shit out of those devices and they still work. What about laptops? Would it be a good idea to use a solid state hard drive on a laptop versus a magnetic? Morgan's shaking his head and Adam's shaking his head yes. Why? You move it. And I don't know how many times I fixed people's computers over and over, and I say, well, your hard drive's shot and we have to buy a new one. The computer's only like a year old. And I say to them, when it's turned on, processing data, moving files around, are you moving around too? Yeah. It's a portable device. That's why I bought my laptop. If I need to go to the bathroom and I'm on my computer, I'll take it with me. So I said, all right, well, we got to replace it. And they're wondering, well, why is that? Your hard drive, like I said, has these platters, these disks. Above these disks, literally, if you take your hard drive apart and a piece of dandruff would fall on that platter, you would literally crash the hard drive. Because what we call these read-write heads are hovering over the surface of the disk 1/10 the diameter of a hair. I think it's 1/10, give or take. Maybe it's 1,000. Are you guys getting the point? It's really close. Now think about this. Hold your arms out and leave them suspended like this, because that's what's happening to your hard drives. They have these arms and they're suspended over these platters. What do you think is going to happen over time? Yeah, they're going to start coming down. But what would happen if somebody starts shaking me? And those drives are spinning. So I have my arms out, I touch the drive, and I dig into it. I scratch it. And they're very microscopic. But over time, you're going to get these digs and digs and digs to the point where you're going to damage something that means your computer doesn't boot up anymore. It'll say files corrupted. Have you guys experienced this with your laptop? When you go to boot up, it'll say corrupted file, can't load Windows. Or when you go to open up a file, it takes forever and then it crashes. Because it has to read it off that storage device and you dug it right out. So if you want to keep your laptop for a longer period of time, I always opt for a solid state. In fact, I will lower it to like 120 gigabytes to make it more affordable for my laptop. And if I need anything more than that, I'll plug in an external device or hook it up to a network. You see this give-take stuff? Desktop, I'm not lugging that thing around to the bathroom when I need to go. Not so easy. So I'll add those magnetic drives. What I'll also do is I'll keep them cool so that they last longer because they have bearings just like your car. Whoa, that's sort of nice of them. Add another hard drive, add another hard drive, add another hard drive. Ask me about that on Thursday. It's called RAID, and we'll explore that. And let's not get about the graphics. We'll get into that later. But what I want to try to get out to you is look how they organize their site. Processor first, memory second, hard drive third. Do you think there's a reason for that? Out of those three things, what is the number one thing that affects the process or the performance? Processor. Out of these things over here, we covered 3 items on there. This one we didn't have much of a choice. It's an Intel processor. So let's call it 1, 2, 3, 4. Then we get into memory. I'm a little disappointed that they didn't list the megahertz in the memory, but I can always hit learn more. And there it is. I also want to bring to your attention, and let me blow it up for you so you can read it. Do you see that this RAM for the 3.2 gigahertz is about a gig? Is that all right? 1066 megahertz. Do you see that the 3.33 gigahertz processor, look at the memory speed. Do you see the memory speed's up more? Beautiful relationship. They scaled it correctly. Why do I say that? Because this is measuring how fast the data can get from memory to the cache, correct? If you have a faster processor, that means it's going to be clearing out this cache faster, correct? And you need to load that cache in as soon as you possibly can. This one will drag its heels. This one will go faster. This past summer, I was building a deck and I had 2 teenagers working with me. Now, you know what the reward for success is? More work. I was up on this deck and I had everything down below me and I had another person up with me. I put the good worker down at the bottom fetching everything. I put the one that dragged his ass right alongside me. Why? Because I really don't like standing 12 feet up in the air as long as possible. If I can get off that ladder as quick as I can, I want to do it, right? So the poor worker would drag his ass, literally, to go pick up a board and bring it to me. The conscientious good worker would run over, grab that board, and run back and grab it to me. And he would keep on loading it. And I loved the slow worker because he was taking his time getting those boards put up on the joists while I was screwing them down. You see the relationship there? I was getting them laid down. Somebody was bringing them to me on the deck, and another person was feeding this person. I wanted to keep that person busy, so I put the fastest worker down on the ground grabbing the boards. That's what's happening here. We want to keep that memory loading up the processor. Does it make sense to put this speed of memory next to that processor? You might get a 1 performance gain. Would you have a negative effect by taking this one and pairing it with that processor? Absolutely. Do you see there's a harmony now? Yes, in most cases, bigger's always better. However, try to match it so you minimize your bottleneck. You increase your performance per dollar, or price per performance, correct? Let's go to another store. I'm not encouraging this company either, okay, folks? And let's see, which ones we want. Are you going to give me... Let's pick... This looks good. Wow, big price difference. $1,000 versus $2,000. First of all, let's look at the processor types. They're using i7s. The other one was using Xeon processors. I don't know if you caught that, but that's beyond the scope of this class. Let's compare apples to apples. Up to 3.9 gigahertz. The fastest one over there was like what, 3.3? So far that's looking sexy. Ah, look at that. 64 bits. Is that necessary for this configuration? By the way, the exam questions are like this. You would get computer specs, and I will ask the question, is this 64-bit Windows necessary for this configuration? And look how appropriate it is. What is the maximum amount of memory a 32-bit Windows or operating system can handle? 4 gigs. What's coming with this computer? Oh, we don't need your help. I'm doing your job right now. All right. What's the maximum? I'm sorry. What's coming with this computer? 12. Luckily, they did the thinking for you, but little heads up. On the exam, I might change one of those two. Okay? And I'll ask yourself, is that appropriate? Okay? 64 can address well beyond the 4 gigs. Whoa. We said the other one was 1,000 megahertz, give or take, and then what, 1.3 or 1,333 megahertz? Look how fast this puppy is. I'm scratching my head and saying, why the hell would I spend $2,500 when so far things are looking better? I'm getting 2 terabytes. Plus, I'm getting SSD cache. What have we learned about cache? By the way, I think this is brilliant. We call these hybrid drives. What have we learned about cache? What's the other name for it? They're waiting rooms, correct? This is for data to be processed, or information waiting to be transferred over to memory, correct? This is a magnetic hard drive. I know because it says 7,200 RPMs, correct? I said that's going to be spinning really, really slow, if you will. But that could be spinning all day long and transferring your frequently used apps over to this cache area. And it's SSD. What did I tell you guys about SSD? Really fast. So now when I connect this hard drive to my motherboard, it's probably going to be at 6 gigabits per second. This is no different than what you guys do when YouTube is constantly dropping frames. You pause and you wait for the gray bar to build up, correct? Data comes from the magnetic to the solid state so that it can be transferred faster. A lot cheaper this way. You get the storage, you get the warehouse, you get the room to store things, and you get the speed benefit. This computer's looking really sexy. Then I'm coming down here and I'm looking at the graphics card, which we'll explore later, but there's a 7 there where the other one had a 5, correct? Exactly. And we'll get into video memory, but right off of that, let's customize this. By the way, it said up to. So I bet you the $900 or the $1,000 is probably the lowest configuration, so the lowest memory. Let's see. I don't get a choice now. It's 64-bit. Great. Let me continue to personalize this. Oh, forget about Office. Forget about the monitor. We'll explore what to look for in there. All right. So I am getting 12. If you're going to be doing more, I'd recommend more, right? By the way, if I was buying this computer, I wouldn't upgrade from here. Remind me on Thursday's class to show you how easy it is to upgrade memory on a desktop computer, even on a laptop. I could probably buy that for like $50 somewhere else. Just to show you that it's really cheap and it's really easy. All right, so we have 2 terabytes plus that's built into the price. I'm really liking this, guys. By the way, they're giving you an idea of how much you can store. I believe in your last lab, which is graded and handed back to you guys, tells you how I asked you, like, what are the size of things? Their approach is you can store 570,000 photos on this hard drive. And if you're not into photos, but you're into music, 500,000 songs. And if you're not into music, but you're into videos, 240 hours of high definition. That's a lot of laundry. All right, by the way, transfer speeds, did they show that here? 6 gigabits per second. Very wise. It's in nice harmony. Don't worry about the graphics card. Did they say anything about the processor? Did it have a choice in that? No, they didn't give me a choice in the processor. Yeah, all right. So those are the three components. It looks like I'm stuck with that 3.9 i7 processor. What do you guys think is a better buy?
The Dell.
The Dell? So what do I gain by spending an extra $1,500 with Apple?
The name.
I'll see you guys class on Thursday. We'll explore software later.